Okay, so we're going to get started with a little bit of review of what we talked about last year. So starting off with history of our atom. Starting off with that Greek philosopher Democritus we talked about. He had this idea that like everything was going to be made up of these small indivisible things. He called atomos, which just means indivisible in Greek. We just call this atoms now. That's where we get that word from. His problem was this other Greek philosopher, Aristotle, had these three big questions for him. First being, if we're all made up of atoms, like what holds those atoms together? So if I have a bunch of like atoms, these small indivisible things, what's stopping one of those atoms from like breaking off and kind of going off on its own? Essentially, like if there like some unseeable force going on that holds things together. His second question is like, why can't we see these atoms? Right? We can see like grains of sand in a beach. Why can't we see these small indivisible atoms that they talked about? And the last question was, well, what kind of holds structures together? Like, why don't we fall down like a bag of marbles? So like, what keeps the structure of these things together? So because of those three questions, this idea of the atom kind of died out until Dalton came along and he kind of revived this marble theory of atoms. J.J. Thomson came up with the cathode ray experiment, which is essentially just a big glass tube connected to a battery that had an anode and cathode, like this negative and positive plate in there. He fired these cathode beams, which is basically just electrons, through this tube, and he was kind of just seeing where that beam of electrons kind of went. So if it's just a cathode ray, that beam is going to go straight. Kind of what he expected. He then put a magnet next to it. So if that negative part of the magnet was next to the beam, it would deflect that electron beam away from the magnet. If he put like a negative and a positive plate next to that cathode ray, that electron beam would kind of get deflected away from the negative towards the positive. So it kind of gave him an idea that this like beam of, well, he didn't know electrons yet, but this beam of negatively charged things is going to exist for electricity. Building on this, one of his students, Milken, developed this Milken oil drop experiment, which kind of just built on Thomas's data. All he was doing is taking little oil droplets and an atomizer. Atomizers are just like the little parts of like perfume and cologne bottles that kind of break down your liquid into like smaller droplets. And he let this oil droplet go through this container that was being affected by radiation, and it was kind of just measuring how that oil droplet was falling. From these two experiments, we get these two quantities for electrons. We get electron mass and electron charge. Now, these numbers are going to be super, super small numbers. The mass was at 9.1 times 10 to the negative 28 grams. And your charge is going to be negative 1.6 times 10 to the negative 19. Now, these numbers you don't have to memorize. Big idea here is that these scientific notation numbers are super small. So just focusing on the mass, that negative 28, just means that there are 27 place values before you get like the first number that pops up. So we're talking about really, really small quantities. Again, these numbers you don't have to memorize. We're going to simplify them later. So we get this idea of electrons from J.J. Thomson and Milken. Our mass, that was that 9.1 times 10 to the negative 28 grams, we're going to simplify that. So rather than thinking about that super small mass every single time, they created this thing called atomic mass units, or AMU. So our mass, since it's such a small number for electrons, our electron mass, we just simplified to 0 AMU. It doesn't really weigh anything. Now, we saw it does have a mass, but compared to like the other parts of an atom that we'll talk about later on, that mass is going to be relatively insignificant compared to like protons and neutrons. Our charge, again, we're going to simplify that. So our charge for electrons is going to be just -1. And again, we're talking about this atomic scale. Building on this idea, we have these negatively charged particles. But what about positively charged? So we have Goldstein's experiment, who took a Crookes tube. Essentially, it's the same thing as a cathode ray tube. You still have the anode negative plate, cathode positive plate. Only difference here is that in your cathode, you have these small holes in that plate. So he took hydrogen atoms, charged them, shot them through that tube, and he was looking at how that hydrogen atom kind of broke apart. He saw that some of the negative charges were moving in opposite directions from like these other things that must be positively charged. So he kind of took this data and he came up with this understanding of atoms, or of protons. So for our protons, we're going to have a similar breakdown. That mass, 1.67 times 10 to the negative 24. When we compare that to electrons, the 9.1 times 10 to the negative 28. You see it is still a super small number, but relatively it's a lot bigger because that negative 24 means there are 4 less zeros or 4 less values before we get to that electron value. So when we kind of round that up in our atomic mass unit, we just define that as having an atomic mass unit of 1. So for our protons, our mass is going to be 1, our charge is going to be positive 1. It's kind of like opposites of electrons. Well, now that we have this idea of like positive and negative charges, so J.J. Thomson's going to come around and he's going to kind of create a big picture for us. So where we had Democritus and Dalton have this marble idea of like just a solid thing, Thomson's going to take this information about positive and negatives and he's going to develop this plum pudding model. So we still have that base of a marble, but now our marble is going to be positively charged. It's like the atom is a positive thing. Within that positively charged atom, we have these like little negative charges on the inside that we can kind of break off sometimes in those cathode ray experiments. So this plum pudding model, the atom is positive and it's made up of little negatively charged things. Rutherford kind of built on this in his gold foil experiment, and he took this big block that had a radioactive source inside, and he was letting radiation come out of that. So we have this thing called alpha radiation. We'll jump into radiation a little bit later. For now, alpha radiation, you can just think of like helium atoms, which are kind of big compared to the hydrogen stuff we've been talking about before. So these helium atoms that are charged are just going to move forward, and assuming that this gold foil is like this solid thing, it shouldn't pass through. But we saw a couple different results from this experiment. First and most common is that radiation would go straight through the gold foil and hit the detector. So it's almost like that gold foil wasn't even there. Based on this, we kind of got this idea that atoms are going to be mostly empty space. So if that plum pudding model was true, that positive solid atom having small negatively charged parts doesn't really work anymore. The second outcome was that the second most common thing you saw was those beams would get kind of deflected at small angles. So they would still go through the gold foil, they would just get pushed apart. So thinking about the cathode ray experiment, that beam would get deflected away from negatives towards positives. So that small deflection angle kind of told us that, well, there is this still positive thing in the middle. It's just not as big as we thought. Otherwise, we'd see a lot more deflection happening. And then the least common outcome was those alpha beams would bounce straight back. It's almost like it was actually physically hitting something and getting deflected back away from that thing. Well, if it was just this electron that it was hitting, electrons have no mass, so if like you hit it, it would just be pushed apart. Because again, we're talking about helium atoms, those things are kind of heavy. So it must be hitting these small positively charged things that are all packed in together. And that's where we get this idea of the nucleus from. So with that gold foil experiment, another scientist, Niels Bohr, took this hydrogen or helium atom and added a bunch of energy to it. So this is super similar to the colored fire experiment we did last year. And what he saw was that he was getting different emissions of light or different emissions of energy from that atom. So based on a bunch of math he did, he kind of saw that he could calculate how far away those electrons were from your center of your atom. And this really broke two of the big assumptions that classical mechanics kind of had. First being that electrons aren't kind of just placed inside the atom. These electrons were actually kind of moving around in an orbit, almost like planets. The second violation to the classical idea was that you could actually calculate and figure out different distances of electrons in atoms, and those distances had energy levels. So almost like rings of electrons. If you knew how much energy was like released based on the color, you could calculate how far away from the center of the atom those electrons were. And now we're running into a problem that, well, now we know that the center of the atom is packed with a bunch of positive charges. But if all these positive charges have the same charge, and we know like the same charges will repel from each other, that first question that Aristotle brought up, well, like what's going to hold this thing together? And there's this thing called the strong nuclear force that holds it together. The idea being that there needs to be these like neutral molecules, like act like kind of like a buffer that keep the positive charges far enough away that they don't really interact very much. That you're interacting more with these neutral charges. This is what we call that strong nuclear force. And it worked up until we get to element 82 on the periodic table. That's where the strong nuclear force kind of starts to break down. So you can think about it like blowing air into a balloon. That balloon's going to get bigger and bigger and bigger until it reaches a point where you can't fit any more air in there and it's going to pop. For atoms, if you fit too many protons and neutrons inside your atom, it's going to start releasing radiation. So we have that alpha radiation that we talked about earlier. You have gamma, beta. Again, we'll talk about radiation later on. Big idea here being that that strong nuclear force kind of breaks down at element 82 for reactivity. And this is where we get this idea of neutrons from. So James Chadwick kind of takes all this data together, does a bunch of calculations, and we get this idea of the neutron, where your neutron is going to have a mass that's exactly the same as protons. So again, putting it in that atomic mass unit, our neutron mass is going to be 1. Neutrons are going to have no charge. They're neutral. So to summarize really quickly, we went from that Greek idea all the way up to this like planetary model. So to do that, we discovered that, well, the middle part of your atom is going to have protons and neutrons. On the outside, you have electrons that are kind of orbiting almost like the solar system. And that strong nuclear force is going to hold your atoms together up until 82. And that's where you kind of pop and start releasing radiation. So from the Greek and Dalton reviving that Greek model, we jumped into positive negative charges with the plum pudding model. And then from that, Rutherford's experiment gave us ideas that, well, you have like this positive middle, and then everything surrounding the outside is like negative electrons, and they're kind of fixed in location. Then we add that electrons are actually moving around, like orbiting around in our planetary model in like fixed locations, and the farther away you are, the more energy you have. And in a later lesson, we'll add and jump into our quantum model. But for now, we got to talk about a little bit of math we can do with our atoms. So there are these things called isotopes. Isotopes are just going to be different variations of an atom you're looking at. So if I have these two isotopes of chlorine, so chlorine 35, chlorine 37, these are just two chlorine atoms. And in this question, it wants us to write, for the first part, the complete chemical symbol for the chlorine elements. So in step A, I need to set up something called isotope notation. So we said an isotope is just an atom with a different mass. It's like a variation of an atom. So if I have like the isotope notation, I'm going to start with a chemical symbol. I'm just going to put X as an example. It's like a general thing. On top of that chemical symbol, I'll have some number. That will be my atomic mass. And then on the bottom part of that symbol, I will put the atomic number, which is just the number of protons. Right, so same thing we did last year. So writing that atomic symbol for chlorine, chlorine is always going to be the same. So if you pull up a periodic table, we can take a look at chlorine, like the normal chlorine there. So chlorine is going to be number 17. So your first step is find the atom on the periodic table. So that atomic number is going to tell us our number of protons, which is going to give us that bottom part of our symbol. Step 2 for our chemical symbol is going to be to set up that isotope notation. So again, our isotope notation has our chemical symbol. That's going to be chlorine here. So I'm going to put Cl. On top, I'm going to throw my atomic mass. So I have 2 atomic masses here. Our first atomic mass is going to be 35. So I'll put 35 on top. And then our number of protons is going to be 17. So that'll be for the first chlorine. So what I'm doing here is it's saying Cl35. In the format, that Cl is the atom I'm looking at, and that 35 is going to be the mass. So all I'm doing, taking that mass, throwing it on top of the Cl. Here it gets to give us 2 isotopes, so Cl37 is the other one. So I'll write the isotope notation for that chlorine as well. So on top, I'll put that 37. On the bottom, my atomic number, 17. So those will be the chemical symbols for those 2 isotopes. And that'll be part A. Part B is asking you to give me the number of subatomic particles. So part B. Number of subatomic. So we have 3 subatomic particles. You have your protons. You have your neutrons. And you have your electrons. So your protons and electrons, for a normal neutral atom, which for the most part isotopes that's what we're going to be dealing with, those 2 should always be the same number. Your neutrons we're going to get from the atomic mass. So if you have your atomic mass, if you subtract the number of protons, you should get number of neutrons. Because again, if you think about your subatomic particles, your proton has a mass of 1, neutrons have a mass of 1, electrons have a mass of 0. So if you know your mass, that's going to be a combination of protons and neutrons. So if you subtract the number of protons from that mass, you'll be left with just neutrons. So let's go ahead and do that for both. We have our first isotope, the Cl35, and our second isotope is Cl37. So we'll set up our little table underneath. And let's calculate that. First numbers are easy. That bottom number is your atomic number, which is your number of protons. So 17 for both. Well, I know for a neutral atom, I just don't see any charges given here at the top. So I should have the same number of electrons for both. Now this is going to change for the neutrons for both. My atomic mass is on top, so I'm going to put 35. My number of protons, we said, was 17. So I'm going to subtract that. And that should give me my number of neutrons. So I'm going to take 35, subtract it from 17. And it should give me my number of neutrons. And I'm going to do that for both isotopes. So same thing for the other one. I'll do my 37 minus 17. That bottom number. And that'll give me my number of neutrons as well. So it'll be 20 there. And it'll be 18 here. And that'll be for part B. And then our last part, for part C, it's asking you to calculate the average atomic mass. So for part C, average atomic mass. So I have these two isotopes, right? Chlorine 35. And I have chlorine 37. In the question, it's telling me chlorine 35 is 75.78%. So that means like roughly like 76% of the time, if you had like 100 chlorine atoms, that 3/4 of the time you're going to find that chlorine 35. So I'm going to bring down those percentages as well. So that'll be 75.78. And chlorine 37 is going to be 24.22%. So that's basically the abundance. So what I'm trying to do is figure out how common each isotope is. So the way I'm going to do that is I'm going to take a weighted average. So in that first step, I'm just kind of figuring out my numbers, kind of copying them down. In my second step, I'm going to take that weighted average. So what I'm saying, a weighted average, all I'm saying is you take the abundance, and I'm going to be multiplying it by the mass. If I do that, my abundance is going to be like how common it is, and my mass is going to be telling me like how much there is. So by multiplying how common it is times how much mass there is, the weighted average I'm calculating is going to tell me, like on average, the weight I'm going to be seeing every time I grab like one of those chlorine atoms. So for chlorine 35, let's do that math. So our first step is we're going to take that percentage, the 75.78%. I'm going to convert that into a decimal. I'll do that by multiplying it by 100. And I'll get 0.7578. So I'll take my 35, my mass, and my abundance, and I'll multiply those two numbers together. So if I do that, 0.7578 times 35 is going to give me 26.523. And if I do the same thing for my other chlorine atom, it'll be that 24.22%. I multiply that by 100 to turn that percentage into a decimal. So 0.2422. And I'll take that number, that abundance, multiply it by that mass to see how common I'm going to see that mass carried over. And I will get 8.9614. And those are going to be my weighted averages. So my third and final step for this problem, I'm going to add my weighted averages together. So if I take my weighted average, and I'm going to add that to my second weighted average, I will get my total mass, or my total average mass. So if I do 26.523, add that to 8.9614, again, this mass here was from my Cl35. This second one was from Cl37. If I add these two together, I would get 35.48. And that would be like my average mass of chlorine. If you look at the periodic table and you find chlorine, that average mass of chlorine is going to be 35.453. It's like super close. And that's how you're going to do isotope math. If there was 4 isotopes, you would get 4 weighted averages, add them up, and it would be the exact same process. So that's kind of all the big ideas for isotopes. Isotope notation, chemical symbol, atomic mass on top, atomic number on the bottom. That can get you your subatomic particles. Protons, electrons are the same for a regular atom. Find neutrons is atomic mass minus atomic number. If you get multiple isotopes, you can figure out how common each one is. All you need to do is create a weighted average, which is just multiplying your abundance times your mass. That'll give you a bunch of weighted averages. Just add up all your weighted averages and it'll give you your total mass. Now, a variation of this problem you might see is if I told you your total average mass was 35.48, and if I told you that chlorine 35 was at 76% abundance, I could ask you to calculate the abundance of the other chlorine. Now, obviously, you could say like 100%. So 76 minus 100 would give you that 24. But the other way you would do it is you take these two, you'd multiply it together, get yourself your weighted average. So that'll be your weighted average here. I know if I add that, that should be my second weighted average. So if you actually multiply those two numbers together, for this chlorine that you do know, you would get that 26. And you would say, oh, okay, Well, I know that weighted average is 26, so if I subtract 26 from both sides, that weighted average would cancel out. You would get like 8.9 left over. 8.9 would be your weighted average for chlorine 37. And then you would say, okay, well, I know my weighted average is 8.9. My mass is 37. And your weighted average is just your mass times your abundance. So if you divide both sides by 37, you'll get like 0.24 should equal your abundance. And then if I want to turn that into a percentage, multiply by 100%. So you'd get 24% as your abundance of Cl37. Right, so that's just how you go both ways. If I give you all of your abundances, weighted average, add up all your weighted averages, gives you your total mass. If I set it up where I give you your total mass and I give you one of the abundances, the way you would calculate the missing one is going through this process of like weighted average, subtract that from your total. It'll leave you the weighted average of whatever you have left. Well, you know weighted average is mass times abundance. So get abundance by itself. Gives you your abundance. And then if you want to turn it into a percent, just multiply by 100. Gives you 24%. So that's how you go both ways for this isotope math.